So our next speaker is Dr. Oorna Mitra from Chennai Mathematical Institute, and she will be speaking on the conjugacy problem and other related algorithmic questions in solvable Baumslag Solitar groups. Yeah, over to you, Oorna. You may begin.
Thanks, Shomo, for having me. So I'm going to talk about the conjugacy problem and other related algorithmic questions in solvable Baumslag Solitar group. So here's the plan for the talk. So in the first part, I'm going to define the conjugacy problem and also the word problem, which are classical. They are known as the fundamental decision problems in group theory. And some other related algorithmic questions in groups, namely the twisted conjugacy problem and orbit decidability. And in the second half, I'm going to tell you how these questions are related. So this conjugacy problem, twisted conjugacy problem, and orbit decidability, how they are connected, which is a strategy developed by Bogopolski-Martino-Ventura. And in case you're interested, you can find it in the paper named Orbit Decidability and Conjugacy Problem for some extensions of groups, which appeared in Transaction of Amers in 2010. And then finally, I'm going to talk about a work in progress with Mallika and Enric Ventura, where we attempt to solve the conjugacy problem in certain extensions of solvable Baumslag Solitar group using the strategy developed by these three people. And what I'm going to do is that I'm going to state some results that we came up with. And we are yet to reach the goal which we set out for, but I'm going to talk about the progress that we made and the observations and all of that. So let us begin with group G finitely presented, which is given by its presentations. AIs are generators and RIs are relations. Now, most often groups are described in such fashion, and it's indeed a very nice and neat way of describing a group. But then group presentations has big disappointments too. For example, it's not at all easy to recognize a group from its presentation. So which brings us to the fundamental decision problems in group theory, which were introduced by Den in 1911. So the first one which is called the word problem. Here we have a given presentation like this, and the question is to find an algorithm which takes a word in the generators, AIs, as an input and gives an output yes or no, depending on whether the word that is the input is equal to the identity element in G or not. So even this apparently innocent looking problem is not so innocent. In fact, there exists finitely presented group with unsolvable word problem. That is, there exists finitely presented group for which no such algorithm exists. Okay. Now, the next one is the conjugacy problem. This is the one that we are interested in this talk. So once again, you are given a presentation like this. And the problem is to find an algorithm which takes input two words, U and V, written in terms of the generators as a product of AIs and AI inverses, and gives output yes or no, depending on whether U and V are conjugates in G. That is, V is equal to GU G inverse for some G in G. Now notice that if you have such an algorithm for a group, then if you feed that algorithm in input U and identity in place of V, then the algorithm decides whether U is conjugate to identity, which means U is equal to the identity. So that means the algorithm actually solves the word problem as well. So the observation is conjugacy problem is solvable, implies the word problem is solvable. And as you can guess, since this conjugacy problem involves a lot of variables, it is way harder than, way more complicated than the word problem, which is indeed the case. So there exists finitely presented groups with solvable word problem, but unsolvable conjugacy problem. So these are the classical problems in group theory introduced by Den. There is one more which I'm not going to talk about, and all these things are basically motivated by topological notions. Anyway, so let us talk about a few more related problems. The first one is the twisted conjugacy problem. Here, once again, you are given a presentation like this, and you are asked to find an algorithm which takes 3 inputs this time. First one is an automorphism of G phi and 2 elements U and V from the group, and gives an output yes or no depending on whether U is phi twisted conjugate to V, that is V is equal to GU phi G inverse for some G in G. Now notice that once again, if you have an algorithm for this problem, and if you give input U, V in G, and in place of phi, just give the identity automorphism, then that algorithm solves the usual conjugacy problem. So the twisted conjugacy problem in G is solvable implies the conjugacy problem in G is solvable. And as you can guess, the converse is not true, which is indeed the case. There exists finitely presented group G, which with solvable conjugacy problem, but unsolvable twisted conjugacy problem. Now, here are some examples.
Je suis en Inde, donc je préfère pas utiliser mon téléphone. Est-ce qu'on peut se parler sur WhatsApp ou quelque chose comme ça?
I couldn't hear at all.
Bon. Vas-y, je t'écoute.
There's some echo.
Yeah, can you repeat once? Or maybe you can write in the chat.
Yeah.
Yeah, please. Thank you.
Okay. I'll go ahead. Please write in the chat. Okay. So here are some examples of groups with solvable twisted conjugacy problem. Finitely generated abelian groups, finitely generated free groups, surface groups, braid groups, Thompson groups, etc. And then the final decision problem that I would like to introduce is called orbit decidability. So here, once again, you are given a presentation like this, and you are looking and also a subgroup of the automorphism group of G. Okay. And you are asked to find an algorithm which takes 2 inputs, which are 2 elements of G, U and V, and gives an output yes or no, depending on whether U is conjugate to phi of V in G for some phi in the subgroup of odd G that you started with. Okay. Now notice that if you take the subgroup of inner automorphisms of G in place of A, then OD of A, orbit decidability of A, which is the inner subgroup of inner automorphisms, is actually the conjugacy problem for G. Right. So here are again some examples, like for example, finitely generated subgroups of automorphisms of F2 are orbit decidable, but there exists orbit undecidable subgroups of odd Fn for n bigger than equal to 3. Okay. Then finitely generated subgroups of odd Z2, which is GL2Z, are all orbit decidable, but there exists orbit undecidable subgroups of odd Zn, which is GLNZ, for n bigger than equal to 4. So these are some examples. Okay. So now let us begin the second part of the talk, where I'm going to tell you how these problems are related. So we start with a definition, and we start with a short exact sequence of groups like this. Now notice that this alpha F, this is normal in G. So whenever you take a conjugation inner automorphism of G that restricts to an automorphism of F. So for every G in G, P of Gx, which is defined as Gx G inverse, is actually an automorphism of F. Not necessarily inner, but definitely an automorphism of F. Now let us collect such automorphism of F and call them AG. This is a subgroup, yes, and it's a subgroup of odd F, and this subgroup is called the action subgroup of the given short exact sequence. Okay. So basically, given a short exact sequence, you have a subgroup of odd F, which is called the action subgroup corresponding to the given short exact sequence. Now, here's the theorem by Bogopolski-Martino and Ventura. So let me first state the theorem and then I'll explain. So suppose we have such a short exact sequence of groups given by finite presentations. So all these groups involved in the short exact sequence, they are all given in terms of finite presentations, and the maps involved in the short exact sequence, they are given by images of generators, such that F, which is the group on the left, it has solvable twisted conjugacy problem. H, which is the group on the right, this is torsion-free hyperbolic. Then the group in the middle, G, it has solvable conjugacy problem if and only if the action subgroup, which is a sum of OT F, is orbit decidable. Okay, so now let me say a few words about the theorem. So what this theorem essentially does is that it reduces the conjugacy problem in G to the twisted conjugacy problem and orbit decidability problem in a normal subgroup of G, right? But then, as we have noted before, twisted conjugacy problem is in general harder than conjugacy problem, and orbit decidability problem can also be quite difficult and tricky. But then this time they are taking place in a subgroup, right? And not in the whole group G. So in case the subgroup F is significantly easier than G, then this theorem becomes quite helpful. It reduces the conjugacy problem in G into two independent problems, maybe more technical, but in an easier group this time, which is F, right? So this is one way of thinking about this theorem. And the other way that you can think about this problem is that in the virtue of this theorem, it becomes interesting to collect groups which have solvable twisted conjugacy problem. So, and for every such group F, it becomes interesting to study the orbit decidability of subgroups of OT F. Every finitely generated subgroup of OT, once we know that F has solvable TCP, then every finitely generated subgroup of OT F gives rise to an extension of F, which has solvable conjugacy problem. And every orbit undecidable subgroup of OT F gives rise to an extension of F, which is unsolvable conjugacy problem, right? So, and this is the strategy that we are going to adopt in our attempt to solve the conjugacy problem in certain extensions of the solvable Baumslag Solitar group. So in our case, F is going to be the solvable Baumslag Solitar group. And we are interested to understand the conjugacy problem in extensions of solvable Baumslag Solitar group. In light of this theorem, what we are going to do is that we are going to study the twisted conjugacy problem and orbit decidability in the solvable Baumslag Solitar group. Okay. So that's the plan. Okay. Now let us look at the solvable Baumslag Solitar group. So these groups, you can define them for every non-zero integer n. They are denoted by BS1n and defined by, so there are two generators A and T and only one relation. TAT inverse is equal to a power n. You can think of it as an HNN extension of Z, which is generated by A relative to Z, NZ, and phi, where phi is a map from Z to NZ defined by phi of A is equal to a power n. Now here's the normal form of elements in BS1n, which follows from the normal form of elements in HNN extensions. So any element G in BS1n can be uniquely represented as G is equal to T power minus K A power L T power M for K, L, M inside Z with K and M bigger than equal to 0. And L is multiple of N implies either K equal to 0 or M equal to 0. So what this does is that it gives us a really nice simple way of writing down every element in BS1n. And this is very crucial in all our groups. Now, let us look at this group in a different way. So we have BS1n, which is this group generated by two elements and one relation. We have a natural map from this group to the group of integers, which we can think of as generated by the letter T. So this map sends the generator A to the identity element 1 and sends T to itself, T. So it's easy to see that it's a homomorphism. In fact, it's onto. And let us look at the kernel. Kernel contains all these elements where K is equal to M. Now we can define a map from the kernel to this group Z1 by N. And the map is given, defined in this manner. Turns out that this map is an isomorphism. Okay? So basically what we have is this short exact sequence of group. And this short exact sequence splits. So BS1N is basically a semi-direct product of this group Z1 by N, which is an abelian group, but infinitely generated, and another abelian group, finitely generated, in fact, a cyclic group. So BS1N is a semi-direct product of two abelian groups. So it's meta-abelian. And this description of BS1N is most convenient for us. I mean, we think of BS1N as a semi-direct product like this. Now, let us look at the automorphisms of BS1N. So let phi from BS1N to BS1N be an automorphism, then phi is of a very special form. So phi takes A to this element, T power minus K, A power L, T power K, and phi of T is equal to T power minus P, A power Q, T power P plus 1, where K and P bigger than or equal to 0, LQ belongs to Z, and L divides some power of N. Now, this condition may look a bit artificial. So what this condition does is that it ensures that phi is a surjective map. And since BS1N is Hopfian, it also implies that phi is injective. Okay. Now, from now on, whenever we talk about automorphisms of BS1N, we are going to think of them as a quadruple KLPQ. Okay. Yeah. Now, now we want to understand what is this group. Okay. So the first thing that we note is that there is a map from odd BS1N to Z1 by N star. This is the group of units of Z1 by N. As I told you, odd BS1N, the elements are quadruples by the last theorem. So KLPQ, this goes to L by N power K. Now, clearly, this is an element of Z1 by N. Why does it lie inside Z1 by N star? This is because by the last theorem, L should divide a power of N. Okay, so we have a map like this, and it is actually a surjection. Yeah, so it's a surjective homomorphism. And what is the kernel? So kernel is this, and we can define a map from the kernel to the group Z1 by N by this map. And turns out that this map is an isomorphism. So we have a short exact sequence like this, and it splits. So odd BS1N is once again a semi-direct product, where we have Z1 by N, which is an infinitely generated abelian group. And here you have Z1 by N star, which is a finitely generated abelian group. So odd BS1N is a semi-direct product of two abelian groups, so it's meta-abelian. Now, here are some theorems that we proved. So the first one is that the twisted conjugacy problem in BS1N is solvable. Now, in light of the theorem by Bogopolski-Martino-Ventura, once we know that TCP in BS1N is solvable, it becomes interesting to look at finitely generated subgroups of odd BS1N and check whether they are orbit decidable or not. Because every time we find an orbit decidable finitely generated subgroup in odd BS1N, that will give us an extension of BS1N with solvable conjugacy problem. And every time we find an orbit undecidable subgroup inside odd BS1N, that will give us an extension of BS1N with unsolvable conjugacy problem. Okay. So in that direction, the first theorem that we came up with is that the whole automorphism group odd BS1N is orbit decidable. Okay. But we want to know what happens to the finitely generated subgroups of odd BS1N. That is what we want to figure out. So yeah. So let us, the question is, let H be a finitely generated subgroup of odd BS1N. Is H orbit decidable? So how do we go about that? So the inputs are U and V. which they are elements inside BS1N. So first we check whether we have a map automorphism of BS1N that takes U to V. Okay, this we can check by what, because ORT BS1N is orbit decidable. So we know that there is an algorithm to do this job, right? Now, if not, if the algorithm says that no, there is no such element inside ORT BS1N that does this job, that means there does not exist any element in a subgroup of ORT BS1N that does this job, right? So we can forget about it. But if there is an element in ORT BS1N that does this job, that is send U to V, then what happens? Then we look at the collection of all automorphisms that takes U to V, and we want to know whether one of them or many of them or whatever, they lie in H, the subgroup that we started with. So that is whether this set, the set of all automorphisms of BS1N that takes U to V, whether it intersects H or not. That is what we want to figure out. Yeah. Now, what is this set? The set of all elements in ORT BS1N that takes U to V. This is nothing but a coset of the stabilizer of U. And the representative of the coset is a map phi naught in ORT BS1N that takes U to V. So basically what we want to understand is that given a finitely generated subgroup H in ORT BS1N, does it intersect a coset of the stabilizer of U? So this is the question. And this brings us to the well-known coset intersection problem. So what is this problem? So here, once again, we are given with a presentation of G, and we are required to find an algorithm which takes two subgroups H and K of G as input and also an element of G, X, and gives an output yes or no depending on whether H intersection XK is empty or not. So we are in the problem that we are in is an instance of coset intersection problem, but this is not as general as the regular coset intersection problem, because here H is arbitrary, but this is the other subgroup is of very special type. It's a stabilizer. In fact, what we have shown is that these stabilizers are always abelian, and in most cases they are finitely generated. So here's the theorem. Let G belongs to BS1N, n not equal to 1. Let us, we are not bothered about the case n equal to 1 now, because when n equal to 1, this is BS11 is just Z2. And G is T power minus K power L T power M, be the normal form of G. Then stabilizer of G is finitely generated abelian when K is not equal to M. And in this case, the generators of stabilizers, this is a set of generators of stabilizer is computable. And stabilizer of G is Z1 by N, which is again abelian, but not finitely generated when K equal to M. So what we see is that the stabilizers of every element of BS1N is always abelian. In fact, most cases, they are finitely generated. So here, of course, we are in a coset intersection problem situation, but of a very, very special type. We want to intersect any arbitrary subgroup with a coset of most cases finitely generated abelian group, and we want to understand whether there is an algorithm that decides whether this intersection is empty or not. So right now we do not know how to do this, but we did make some progress, and we feel that there does exist such an algorithm which does this job. And once we prove it, it will enable us to conclude that every extension of BS1N by a torsion-free hyperbolic group has solvable conjugacy problem. So with this, I end my talk. Thank you.
Yeah, thanks, Oorna, for the very nice talk. Any questions?
Yeah, so I have just one. So, what is the advantage of taking the solvable Baumslag or not? Like, what about the general Baumslag?
Yeah. So
The
the
normal
best
form?
part about the solvable Baumslag Solitar groups is that this normal form that I talked about.
Yeah, this because of this
Yeah,
normal form. Okay.
Yeah, so in any HNN, in any Baumslag Solitar group, or in fact in any HNN extension, you have such normal forms, but they are a lot more complicated than what we have for BS1.
Okay.
Yeah,
And the
and
automorphism
that
group
becomes
is
very handy.
also for a general Baumslag automorphism is like okay, like known, right? Automorphism group of the general Baumslag Solitar.
That comes with another set of problems. So there are many Baumslag Solitar groups for which forget about the solvable ones. This we have already seen. For the other ones, there are many Baumslag Solitar groups, BSNM, which have nice automorphism groups. But then there are some which has really wild automorphism groups, like infinitely generated and things like that. But I think, for example, BS24. I mean, if you have BSN, KN, that form, those have infinitely generated automorphism groups. So that's a whole new level of complications. But then there are other Baumslag Solitar groups with nice automorphism groups. Yeah.
Okay. Thanks.
Yeah, any more questions? So while you were saying something, you can. You had some comments?
No, I was not saying anything.
Okay. So in that case, let us thank the speaker again. Thanks a lot, Oorna.